Okay, so what we're going to look at now is expressing or representing endo and exothermic reactions using a model which is called an energy profile, and we also have some key information here. So what an energy profile shows you a couple of things. It shows you where the reactants and products are during the reaction progress. It also shows you delta H, which is again like heat. It's known as enthalpy, and it's similar to heat. And it also shows you what's called the activation energy, which is the energy required to get the reaction started. So whether a reaction is endothermic or exothermic, there's always some energy needed to start the reaction. So let's go ahead and draw our energy profile. The first one we're doing is endothermic. So for endothermic, key thing to know is that the system is absorbing energy, so the energy of the products is going to be greater than the energy of the reactants, okay? So energy of product will be greater than the energy of the reactants. And on our axis, we can see on the y-axis we have energy, and on the x is reaction progress. So I'm going to start with the reactants right here. So our first line is reactant because that's what we start off with. And then we're going to draw a line to the right of that that's going to be our products. Now because this is endothermic, should I draw the line above it or below it? I'm going to draw it above it because for endothermic the system gains energy. So that means that the products have to be at a higher energy, so higher on the y-axis than the reactants. All right. Now we're not going to just draw a line straight from one to the other. We have to draw what's called our activation energy. So you always draw a little bit of a hump, and that's known as our activation energy, sort of like a little hill that links these two. So let's go ahead and fill in now parts of the reaction, what our activation energy, what our delta H is, etc. Delta H will be the energy difference between the products and the reactants. So you're going to draw a line between the products and the reactants, and that's your delta H. All right. Well, let's do a different color for our activation energy just so we can keep track of it. Activation energy is the energy from the reactants to the top of the hill. So I'm kind of drawing it off to the side because I've lost room here, but from the top of this hill to where the reactants are, that difference in energy is our activation energy. So let's go ahead and fill this out. EA, activation energy, energy needed to get a reaction started, and it's the difference between from R top of hill. All right, on the other hand, our delta H, change in enthalpy, it's going to be between R and P. Okay, it's good to keep track of that because both of those are there. All right, so now we're going to try the same thing for an exothermic. So we start off with our R and P, but the thing to remember with exothermic energy is exiting or leaving the system. So the energy of R is going to be greater than the energy of P. That means that R is going to be higher than my first line over here on the left is going to be higher than my product. So in that case, I'm going to put the R, start the R up a little bit higher than I did over here just for room's sake. And I'm going to put my P down lower. So it's exothermic, it's losing energy. Now once again, when I draw my profile, I can't just draw a line straight from R to P. I have to draw a little activation energy hump. And now I can go ahead and draw in my value. So for activation energy, it's from R to top of the hill, so that's my EA. And then delta H is from R to P. Okay, so you're looking at these two. You notice these annotations look a little bit different, but if you follow the definitions in terms of activation between R and top of the hill and delta H is between R and P, you will get it correctly instead of just trying to visualize and memorize it that way. Okay? All right. So these are energy profiles, and the reason why these are useful is that they help to visualize what's happening during a reaction. This activation energy is important not just in terms of thermodynamics, but also in terms of how fast a reaction goes. So a lot of times people look at this to see if a reaction is proceeding fast or slowly. The higher this hill, the more slowly it is. So there's information there. And once again, delta H really gives you a sense about how much energy is needed or is released by a reaction. And in the real world, we use that information for things like how much energy one can get out of fuel, for example. So all of this stuff is sort of used in different ways, and it's really useful, this energy profile, to visualize that. Okay. Last couple of key pieces of information we're going to learn about endo and exo in terms of how do we experience endo and exothermic reactions. So for an endothermic reaction, if you're holding a beaker where an endothermic reaction takes place, the reaction is going to feel cold. And that's because your hand is the surroundings, and the system, which is the reaction, is absorbing energy from your hand. So it will feel cold. So endothermics, even though they're gaining energy, they feel cold. Exo, on the other hand, they feel hot because they're releasing energy into the surroundings. And so if a reaction is happening in a beaker and you're holding that beaker and it feels hot or warm, then you know you have an exothermic reaction happening. And that's really key because that's a quick way for us to do it without using any equipment, just using our hands to see if something is endo or exo. All right, let's take a look at an example here. So melting ice is endothermic, and that's because the ice absorbs heat. So if you want to melt ice, you don't stick it in a freezer. You'll either leave it out at room temperature because that's warmer, or put it on a stove or something like that. But melting ice is endothermic because it's absorbing heat from the surroundings. On the other hand, if you're burning wood, and burning wood is an example of combustion, that's an exothermic process because you will feel the heat being released from that process. So if it feels cold, it's endo, and if it feels hot, it's exo. Okay, there are a couple of CFUs here. So why don't you take a look at the CFUs and pause the video. When you press play again, we'll go over the answers. All right, when mixing sodium hydroxide and water, the beaker feels hot. Is it endo or exothermic? Explain how you know. It's exothermic because the system releases heat into the surroundings or our hands. So if it feels hot, remember, it's exo. Second one, the beaker feels cold. Sketch the energy profile for mixing baking soda and vinegar. So we're mixing baking soda and vinegar, and the beaker feels cold. And we need to label the X and Y axis, which has been done. Energy on the Y and reaction progress on the X. We need to label our reactants and products are, our activation energy, and delta H. Now, in this reaction, let's start with labeling the reactants and products. We know that it feels cold, so that means it's endo. And if it's endothermic, that means that my product line has to be higher than my reactant line. So I'm going to just start by drawing the two lines, this one up higher than this one. So the one on the right is higher than the one on the left. Now what I'm going to do is I'm going to fill in my reactants. So since I have the balanced chemical reaction, I'm not going to just write reactants here. I'll write what the actual reactants are. So that's baking soda and vinegar. All right, on the product side, there are 3 products. I'll just list them all. H2O and CO2. Okay, so I have reactants and products. Next thing I'm going to do is I'm going to draw my little hill, my activation energy hill. So I draw my hill there. And then I can go ahead and start filling in my activation energy, which again is from the top of the hill to the reactants. So that's EA. And my delta H, which will be between my reactants and my products. Okay. All right, so that is it for this. You have an exit ticket that you're going to take on this, and the law of conservation of energy, etc. That will be for tomorrow. All right, that's it, folks.